Hi, in this video, I'm going to introduce you to Dual, diffusing update algorithm. Okay, so this is a convergence algorithm used by EIGRP, and I've mentioned before, the developed and most prominent work done by J.J. Garcia, professor at UC Santa Cruz. So we've got to remember that EIGRP is a distance vector routing protocol. Okay, now it does use other things like features like hold down timers and split horizons similar to RIP, but it uses those in a little different fashion. It uses Dual to be able to prevent loops and have a quick and valid backup path. We're going to see how this works in just a moment. Okay, just show you that there's a Wikipedia link to Dual. Also, there's JJ's webpage and information about some of the other stuff he's doing. Just brilliant man, wonderful guy, great professor, and it's an honor for me to be able to work with him and call him a friend. Okay, enough name dropping there, huh? All right, Dual. Dual is an algorithm used by EIGRP. It determines the best loop-free path, loop and loop-free backup paths, which can be used immediately. Dual also offers very fast convergence because there's a loop-free backup path. Minimum bandwidth used because bounded updates. And the terms that we're going to be using with Dual: successor, feasible successor, feasible distance, reported distance. That's sometimes called advertised distance, but more common now to use the term reported distance, and feasible condition or feasibility condition. Oh boy, all these terms. We'll get there. Okay, there's a Dual finite state machine. This is kind of the finite state machine here. Okay, all the logic. We're going to look at some of this here in kind of a different way, a little easier, I think. Finite state machines, by the way, if you don't know what a finite state machine is, it's a set of all possible states and the events that allow something to transition between those states. There's finite state machines used in all areas of business, science, technology, all sorts of things. Okay. We won't go into the details of the finite state machine, but just to show you what a finite state machine looks like, there's usually a starting point, like hungry there. And the event is if you get food and now you're in the state of eating, that food is not edible or not enough, you go back to the state of hungry. If you do eat enough, you go to the state of full. You stay in that state as the more food you eat. If you don't eat for a while, you get back to the hungry state. That's just a finite state machine. Okay? And if you're really hungry, just go to Taco Bell. All right. So let's take a look at a router R2's routing table. Okay, and what we're looking at is its route to the 172.16.3.0 network in red there. Okay, and this is the world from R2's perspective. Now it's a distance vector perspective, meaning the only thing it knows about the topology is what it hears from its neighbors. Okay, it doesn't actually have a map of the topology. That's a link state routing protocol. All right. So if R1 only knows what its neighbors tell it, for example, R2 says, hey, I can get to the 10.0.0 network in metric of 300. R3 says, I can get there metric of 100. Well, what is the best path for R1? Of course, via R3. But R3 is the best path, but is R2 a valid backup? Can R2 get packets to that network should something happen with the path via R3? Well, that depends. if we have something like this, well, R2 can only get there. Actually, it's learning about it from R1. I mean, the path comes back to R1, so it doesn't have a separate path. But R1 doesn't know this. Okay, so this is what we wouldn't call a loop-free path. It is not a loop-free path because there's actually a loop in it. It loops back to R1. Okay, as opposed to this, same conditions, but again, does R1 know whether or not R2 is a valid loop-free path? Well, it just might be. Maybe that is the path. It is a longer distance, but it doesn't loop back through R1. But again, R1 doesn't know this. And this is what dual does. Dual will only believe loop-free backup paths. Now, how does it determine this? Okay, so in this scenario here, by the way, the top scenario there and the bottom scenario, R1 doesn't know which is the right scenario. It only knows the topology based on what its neighbors are telling it, but how far the distance vector, how far it is from that neighbor to reach that remote network, the destination network. So it doesn't know. So to play it safe, EIGRP only accepts a backup route if it meets something called the feasibility condition. In this case, we'll see that it does not meet the feasibility condition. But let's take a look at how this works. All right, so we're at R2. I'm going to use the command show IP EIGRP topology. We're actually going to look at EIGRP's topology table on R2. And now you see the destination network there, 172.16.3.0. And you're going to see two entries, and we're going to take a look at both of these entries. Okay. The top one is known as the successor, the best path. And in this case, the second entry in blue is actually a feasible successor, a backup path. But we're going to see how it knows that's a loop-free backup path. So let's get started. Okay, so looking at R2, we said that the first entry is known as the successor. A successor is the neighboring router that is used to forward the packet that has the least cost route to the destination network. It's the next hop that we would find in the routing table. Okay, so this is the best path. In this case, well, let me ask you, what router for R2 is the successor for the 172.16.3.0 network? What router is the successor? It's R3, okay, at 10.1.20.3. That's the next hop address of the successor. Okay, so this is the next hop address of the successor. This is the feasible distance. The feasible distance is the routing metric. That is what the slowest bandwidth and the sum of the delays to get to that destination network. And we saw how that's calculated, right, in the video on the EIGRP metric. Now, this value is what R3 is reporting its cost to that network. This is known as the reported distance. This is R3's cost to reach that network. And this last one is this last parameter is the outbound interface to reach this network, the serial 001 interface. Okay, so this is the successor. Now, let's take a look at the next entry, the feasible successor in this case. A feasible successor is a neighbor who has a loop-free backup path to the same network as the successor by satisfying the feasibility condition. We're going to see how it meets that feasibility condition. Okay, it will become the new successor if the successor fails with no packets lost. Let's see how that works. Okay, so first of all, this is the next hop address of the feasible successor, R1's interface. This would be R2's feasible distance. This is the value that would be in the routing table if R1 was the path to this network. And if R1 becomes the new successor, this would be the metric to reach that network for R2, to reach the 172.16.3.0 network. Okay, slowest bandwidth, sum of the delays. This is R1's reported distance to R2. So this is a key value. We'll come back to this. This is R1 saying this is what my routing table says. This is what my cost is, R1's cost, to reach that 172.16.3.0 network. This is R1's cost. Okay. This would be R2's cost. This is R1's cost. And this would be the outbound interface to reach this network if it became the successor. Okay, so the reported distance, like I said, is EIGRP's neighbor's feasible distance to that network. The feasibility condition, and we're going to come back to this, is met when the neighbor's reported distance to the network is less than the local router's feasible distance to the same destination network. You're going, what? Let's take a look. Okay, in red there, we see the successor. That's R2's feasible distance to reach the 172.16.3.0 network, the 3,014,400. R1 in blue there, feasible successor, has a cost of, to reach it, what is that? 2,172,416. For R1 to be a feasible successor, its reported distance at 2,172,416 must be less than the feasible distance in red to 3 million. Okay, so that's a better look. The reported distance in blue by the feasible successor must be less than the feasible distance for the successor. Okay. The only way that R2 can verify that R1 has a path to this network that doesn't loop back to R2 is if its cost is less than R2's cost. Okay. If R1 had a cost that was higher than R2's cost to reach that same network, R2 might think, kind of use my cursor here. So if R1 had a higher cost to reach the 172.16.3.0 network, R2 may think, I can't trust you. Maybe you're coming back through me. That's why your cost is higher than my cost. Because your cost would be higher than my cost if it came through me. If you can get there without coming through me, the only way I can guarantee that you don't come through me is your cost is lower than mine. Because if your cost is lower than my cost to get there, well, you're not coming through me to get there because my cost is, higher than yours. Okay. So R1 says my cost to reach this network is 2,172,000. I'll round it off there. Okay. R2 says my current cost is 3 million. Okay, your cost is 2 million, so that's why you're a feasible successor, because your cost is less than mine. However, if I was to go through you because the path via R3 fails and you're my feasible successor, my cost would be that cost in green, 41 million. You're probably wondering, how come it's so much slower? It's actually the bandwidth here, the 64 kilobits per second. Remember, EIGRP uses slowest bandwidth, sum of the delays. Okay, so it will have one to 3 delay values and this slower bandwidth. Okay. All right. So using a feasible successor, let's see what happens when something happens between the link on R2 and R3. We'll just do a shutdown here. Okay. R2 immediately uses the feasible successor from the EIGRP topology table. So it becomes the new successor. Okay, and R2 will now forward packets to this network via R1. If we do show IP EIGRP topology at this point, we can see that R1 is now the successor. Okay, and if we look at the routing table, our routing table has been updated. And this is really with virtually no packets lost. Happens that quickly. Okay, let's bring that interface back up. Okay, so we have our normal successor R3. All right, now I want to kind of take a look at from R1's perspective. Let's take a look at R1 getting to that same network. Okay, so remember it had a feasible distance, its metric, just over 2 million to get there, down there in the routing table. Okay, let's do show IP EIGRP topology on R1. Now you notice there's a successor, okay, via R3. Notice there's no feasible successor. R2 is not a feasible successor. Why? Well, because it doesn't meet the feasibility condition. Let's take a look. So here is R1, looking at the topology table, okay? All right. There's no feasible successor, okay? Because R2 does not satisfy the feasibility condition. Let's see why. If I use the same command, show IP EIGRP topology, but include the all links parameter, this will show successors, feasible successors, but something else. It'll also show those neighbors that are not feasible successors. Can you see why, from R1's perspective, R2 is not a feasible successor? Look at the reported distance of R2, saying my cost to get to this network is 3 million. And R1 is going, wait a minute, my cost is 2 million. Your cost is higher. Maybe you come through me to get there. Okay, so let's see what happens. Does this mean that R2 can't be used as a backup path? Well, it's not a feasible successor. Okay, so there's a couple more steps involved. Let's take a look at what happens when that link fails and R1, between R1 and R3. Okay. So in dual, when a link fails, if there is not a feasible successor, okay, the router will send an EIGRP update, get an acknowledgement. It will then say, so that just lets the routers know, hey, I can't get there anymore. R1 will send a query saying, hey, does anybody else know how to get to this? Do you know how to get to this network? Okay, this is an EIGRP query, which is acknowledged. R2 will forward the query. In this case, R3 acknowledges it. And R3 says, hey, I'm still here. This network is still here. Sends a reply that's acknowledged. R2 sends the reply, which is the reply for the initial query by R1. And let's take a look at what happens. So what happens is this, and we can actually look at the debug EIGRP FSM to see what happens, finite state machine. Let's shut down the interface between R1 and R3 there. And what happens is R1 will send out the query, not showing all the acknowledgments, but eventually not eventually, but fairly quickly, R3 will send a reply saying, yeah, I can get there. R2 says, I can get there. And so this route will be eventually installed in R1's routing table, the backup. It just doesn't happen as quick as if it was a feasible successor. We have to go through this series of queries and replies. And in large topologies and given sometimes some issues, you know, that convergence might take a little longer than we like. Okay, so I'm just showing you all the debugs here. Always remember to do an undebug all when you're done. All right, so here's the result. Okay, R2 would become the new successor after all this. And we can see that on R1. It says, okay, I've got a new path. Okay, I can see this new successor in my EIGRP topology table, and I see the new path in my routing table. Okay, so it does use R2 as the backup, but it just takes those queries and replies to get there. Okay, we do a no shutdown, so things are back to normal. R3 is now the successor again. We do show IP EIGRP topology on R1, and it says, yep, R3 is my successor, but you know what? R2 is still not a feasible successor. Okay, you know, plays by that logic. You know, just because it used it a few seconds ago doesn't mean, you know, who knows? Things might have changed. It doesn't know. Okay, topologies might have changed. Maybe R2 now it isn't loop free, so it doesn't fall back on the history. Okay, uses logic to make these determinations. Okay, so R1 has the path via R3, and there is no feasible successor. Okay, so I hope this helped you understand a little bit about dual.